right? Like, I am quite fond of using the word sketch in a coded way. So when I say sketch, I almost always mean that I would imagine that you are producing this without the aid of any machinery, right? So if I say sketch the response of this to a step in whatever, I'm imagining you using your brain only for this question and kind of reasoning through it rather than doing any calculations. Or maybe you are doing some minimal calculations to verify behavior. So sketch the response. Now, okay, there's a reasonable chance that this is perhaps not exactly like the way that I would ask in a test, because I would be afraid that many people would simulate this problem instead of doing it in their heads. But I'm going to keep it like this and actually show you how I would do this as a sketch problem without doing any calculations. In a test, I'd probably make this, I would harden this in some way by adding symbols, right? So I instead of having kc is equal to 5 and tau I or tau p equal to 10 like I have here, I may just say it's a pi controller with tau I twice as long as the time constant of the system or something like that. So the idea is that I'm trying to stop you from doing the thing that I don't want you to do, which is like not understand how it works and just simulate it. So I think everybody should understand how you would go about simulating this response, right? So all the closed loop simulation techniques that you know are still there. So this is a first order process under PI control. Probably, I think in a test I may actually have asked something like, what does this look like under proportional only control, and then what will it look like if I add integral control? So a step in YSP, right? And now I want to understand how that difference will occur. And so now I know, let's say from my memory of what step responses look like, I know that the step response of the system itself, this first order system, if I just had normal proportional control with that kind of like high gain, I would expect for a response which would be, so let's say, so with Kc is equal to 5. Now I want you to notice something just in this gain, the gain of the loop here, that the product, and we know that there's this kind of general rule of thumb that the product of the gain in the loop transfer function, from the number of people who are mightily writing that down, clearly that was not a part in the textbook that you read, but it's supposed to be around 1, right? So we know that the forward gain in the loop should be roughly magnitude 1. So the fact that I've got a 1 gain in the system and I've got a 5 gain in the controller tells me this is a high gain controller, right? So I'm using quite a large gain. And so I'm expecting that to be faster, or the response under proportional control only, to be faster than the system would respond to a step response in its input. And so I'm expecting something like this kind of response. I'm expecting not that much of an offset, but with proportional only there will be some. And I'm expecting, like this to be probably, well, less than 10, right? So let's say about 4. It'll be interesting if we simulate this now and see like how close I got. But, so basically, and so this is what I would be looking at when I'm grading this, right? So a lot of students, when they do sketches, is, I've mentioned this before, I'm not looking for an accurate, and this is the mistake that people make. A lot of times when you do a simulation and you get exactly the right response, you may not get 100% for your answer. And the reason is that I'm expecting your sketch to be a caricature. I'm expecting your sketch to accentuate. The goal is not to obtain the response. The goal is to understand whether you understand what features the response will have. Right? So if I say that I want you to draw a picture of somebody who is equipped to chop down trees, I'm wanting to see a chainsaw or an axe or something in that guy's hand, because otherwise, or that girl's hand, right? So cogent features here are things like, if you want to chop down a tree, you're going to need something that you can chop down trees with. Non-cogent features are like what they're dressed as, what gender they are, whether they're tall or thin or whatever, right? Like that doesn't matter. A person with an axe can chop down a tree. And so that's like zooming in on the caricature response, right? And so here again, with proportional only, I'm expecting to have that kind of faster than the open loop response. So the open loop response of that system, right? So the open loop response of that system looks like this. So that's the response of GP to a step in its input. Does that make sense? Right? Because I've got a first order GP, and if I just do a step into GP, I'm expecting it to be slower than the response that I get with the controller, although the controller is kind of also leading to the fact that we're not getting exactly to the output. And then finally, for this question, adding integral control will do exactly two things to the system. It will make the, because I have to remove the negative or the positive parts of the error in the error integral with negative error, right? Inevitably, I will always add some overshoot by adding integral control. So now, even with a first order system, I'm expecting something that will look like this. This is quite a large gain, so I'm expecting probably quite pronounced oscillation and probably quite slow decrease. And my estimate would be that the initial response, so again, if I ask you to plot these at the same time on the same graph, like with the proportional and with the integral, remember that the initial response of the system is pretty much all due to the action of the proportional controller. Does that make sense? Because what happens right at the beginning and you kind of have to think about this in terms of the error. So this is now all in terms of y. Right? But if you think about this in terms of the error, right? The error is largest at the moment that the set point changes. So at that very moment, so remember that YSP is doing this, right? So YSP, and also recall that for the system with no additional information, the only assumption that you can make is that everything was at 0. I haven't given you any more information about real-world variables, so you have no way of relating the deviation variables back to real variables. The best you can do, and I've kind of used the language of linear analysis, right? I've just said, here's a block diagram, here's some transfer functions, what will that response look like? Then at that moment, everything is 0, so all of these things are 0. That's very important as well. So that point there is 0. It's not some other point. And at that moment at which the YSP changes, that's when, at that moment, the error will be equal to 1. Does that make sense to everybody? Because everything was 0. And this is kind of the reasoning that you have to think about. You have to think about this in your brain, not with your fingers or not with your simulation, but like just think about it At the initial condition, everything is 0. Shortly after time 0, at the moment where YSP becomes 1, in that moment, this signal that is being fed back is still 0. And it's going to be quite close to 0 for a while still. Does that make sense? And so what does that mean? The error is equal to 1, right at that initial point, because YSP is equal to 1, this thing is equal to 0, so E is equal to 1. So this is something that I would expect you to add to the sketch, like that fact that it's a 1, it's not just some random value, because you know all the stuff about it, right? Like if you know it's a unit step and you know that it's like at that moment in time, you definitely know what the error is. And recall that if the gain of the controller is correctly chosen, and in this case it is correctly chosen, that's PS. Like another interesting thing to ask in a test, I can give you the wrong sign of the gain and expect you to draw an unstable response, right? Because obviously if the gain of the controller was negative here, the response would be unbounded. It would just go the wrong way. So the error would go up, and the controller would start moving the manipulated variable in the opposite direction, just making the error worse and worse and worse. Okay, but anyway, so the error starts at 1, and at that moment, that's when things start changing. So the controller then makes a move 5 times greater than that error, right? So U So at that same moment in time, U is 5. That's kind of the last place where we are absolutely sure of like the magnitude of these things, right? But in a certain way, that kind of explains to you what we're seeing with the faster response, because what we're actually seeing initially is that same step response, but multiplied by 5. Does that make sense to everybody, what I just said now? So remember, that's the open loop. If that's the open loop step response, right? And U, so that's the step response that we see if U is set equal to 1. That's the unit step response, okay? But now, the error was 1, so U has been made equal to 5, which means that the output will be multiplied by 5. Right? So this is how linear systems work. If I have a unit step response, I also have all the step responses multiplied by any factor that I can imagine, because a step of 2 will cause exactly twice the movement in the output. And so does this kind of make sense in terms of, well, actually that initial response will be like 5 times bigger, right? And so like having a step response and multiplying by a factor will make it look faster. Like it goes further in the same amount of time, right? Like that's what faster means. So it moves more towards 1 in that first bit than it would have. Okay? But as soon as it starts moving, the error goes down. So as soon as the output starts moving, and we can predict this very well without even thinking about the integral, because that initial behavior is all proportional, right? So the initial behavior should be almost exactly the same for the proportional and for the P and the PI, as long as the proportional constant is the same. And as the error goes down, U goes down as well. But remember now, I'm starting to catch up with the integral part. And so very quickly, I'll start taking more action than the proportional controller would have taken at that time. And so basically, if we wanted to plot that, we could say, well, right, the proportional controller would be taking the same 5 and then kind of down, and then obviously just like reaching some equilibrium point. Whereas the PI controller will be taking the same action, but it will then have larger values of the action. Why? Because I'm taking action based on K plus the integral. Right? And at some point, kind of at that point there, that's the moment when the integral starts going down. right? So the integral will go up until that first moment when the error switches sign. And at that same moment, that's when the error goes through 0. Right? I'm seeing a lot of people who don't look like they're following this. So this is not control, guys. Like, I'm literally just reasoning through the mathematical relationships between these signals, right? So as y goes towards YSP, right? Like E is just YSP minus y. So at the moment where y becomes equal to YSP, the error will go from being positive to being negative. Does that make sense? So when y is larger than YSP, that's when the error is negative, because that's when y minus YSP is negative. That's just the straight math. Okay? So this is not like, I'm not tapping any deep knowledge of controllers here. I'm just simply reasoning through like how graphs work with math. So I would expect you to be able to draw these bottom graphs, given the top graph, given y. If I gave you sketches of y, I would imagine that if I gave you that in your second semester of first year, you should be able to produce both of those other graphs. Right? I'm not using control knowledge here. I'm using knowledge about how functions relate to one another. So to your second year self, I would have just said, okay, so here is a drawing that shows, this shows YSP, right? Here are a couple of different versions of y. Draw for me YSP minus y and YSP minus y times 5. Right? So don't make the mistake of imagining that this is some special control-specific stuff. But just remember that you've had a lot of other courses where you drew these kinds of graphs. Okay, so that's now again, if this is not exactly what they look like, this doesn't mean I'm wrong. Right? This would get a 100% mark from me because it shows the things that we know about proportional and PI control in a caricatured way. Does that make sense? Okay. Of course, now I can't ask this in the test. Is by doing this example in class, I've now changed the way that this question works in a test. Right? I've now changed it from a question where you're reasoning stuff to a question where you're remembering that thing I said in the lecture. So I'll find a different way of assessing roughly the same idea. But are there any questions about this? Anybody? You can even Slack on the anonymous or something. I've got my Slack open. But like, does this make sense to everybody? Yes.
Somewhat unrelated, but when you say sketch and you imply qualitative, just to understand, or you use the word like simulate when you want to actually calculate the simulation?
I'll usually say something like, I'm not very fond of asking you to simulate something in a test. I don't know, I don't really see it. It feels like it takes a long time. I'm usually surprised when I see people actually doing the actual calculations. So definitely in a semester test, I'm expecting most of the stuff to be doable. I mean, obviously, if it's something that has a nice finite Laplace inverse or something, I could ask you to do that calculation. I'll be clear. And I think the most important lesson is I'm not expecting you to just be completely without any guidance. If you are unsure about what is expected of you, put up your hand and ask me a question, right? I am in every test. If I believe that this is something that you should know, I'll say so. But you lose nothing by asking. So if you're not clear, if it feels like you could do this analytically or qualitatively, and it's not clear from the wording of the question. You know, so like I say, sketch to me is a very clear sign that I'm not expecting analytic work. Yes?
When the YSP is equal to 1, with the process
Yes. Is I would imagine that when the set point, when this output is exactly on the set point, then the controller should stop acting, or at least at that moment, the output of the controller should be 0. This is true for proportional controllers, obviously. Okay, so let's just remind ourselves of the math. A proportional controller just has U. So for proportional controller, U is equal to KCE, right? That's the whole of proportional controller. And there, 100% for sure, when E becomes 0, U will be 0. Absolutely correct, okay? Recall that for this first order process, the error will never be 0. Okay, because we're going to approach the set point. And that's why I drew for this, that's why I drew here this kind of approach over here. Now that's a sketch, right? So like that's not definitely star, like not to scale, right? It's a sketch. The actual controller output is probably the hardest part of this to sketch, because you kind of have to reason through the integral part as well. So I mean, if I ask you to do that, like I'll give you a lot of marks for all those extra graphs. But remember that for an PI controller, you've got this. For the PI controller, you have U is equal to KC times E plus the integral of E, right? And so because I'm adding that, even when E is 0, the output will still not be 0. Does that make sense? So the controller output will start at some non-zero value, and then I'll be adding to that error integral with a positive error, right? And so you can actually reason through this. Let's do that together. This is the reason why, like in that PID controller output for the TC lab, I've got all of these different components like plotted out in the plotter. So you can see how the error integral is growing, how the derivative is growing, and so on, so that you can kind of aid your decision-making process in how that works. I'm seeing far too many people who appear not to know what I'm talking about. I'm talking about the TC Lab PID that we did in TUT 2, right? And again, I think maybe this is just another example of attentional blindness, because you were so focused on doing the task that you weren't actually paying any attention to any of the outputs. But like maybe revisit it, and you'll see that GUI has all of these things that I'm sketching here, right? It's got the output, it's got the error, it's got the derivative of the error, the integral of the error, the controller output, so that you can see what those relationships are. But let's just think about what the integral of the error would look like for the PI control part, right? So it would start at 0, right? Because we're starting everything at 0. And then it would be growing at a high rate initially, and as the error went down, the rate of growth would go down. And so kind of you can imagine that the integral of the error would be doing something like this. It wouldn't be just climbing linearly, it would be kind of, its rate of increase is going down because error is going down. The biggest that it starts big at the beginning, which means the derivative is large. Remember this, effectively the derivative of that signal, that derivative is equal to this value, right? And so actually we even know that initial slope is equal to 1, right? Because that's the magnitude of the error there. And then it starts going down. At the moment where the error switches sign, we have a change in the rate, right? And so there's a maximum in that error integral at that moment. And as the error then starts going even further negative, this will start going down. And it's this downward, like it's when the error switches sign. Now remember, so we are taking action E plus error integral, right? And so, yes, the error part, the proportional part, has now started pushing the manipulated variable the other way. But the integral of the error is still keeping that action up. And so this is why I've sketched it like the way that I have, that for the PI control, the action of the controller will be above the action of the proportional controller. Why? Because I at least have that proportional part, but then I've also still got the integral part. And because of the integral part, like it's a little bit hard for me to just do this completely in my head with the sketching, so I wouldn't like give you any marks for that. But obviously, it is possible for this integral to catch up to be such that it's as large as the proportional. Now, again, you can kind of imagine, or not imagine, but remember that this tau I is over there, right? That in the actual part, there's the tau I over there. And one way of thinking about tau I, the reset time, is that that's the amount of time given a persistent one error that causes the proportional action contribution to be equal to the integral action contribution. And so, because we've got tau I equals 10, that's kind of 10 repeats. So I'm expecting that to only, it's not such hectic tau I. So if it were 1, right? If tau I were 1, then after exactly 1 second, the integral would be the same size as E if I had just straight, if I just had E coming in. Does that answer your question? Is that clear? Yes?
You could state and disturbance to those responsible similar to the state in
So, look, I mean, you've seen what they look like, right, in the textbook. They are, the key point to remember is that the nature of the disturbance, when I say the nature or the nature of the response here, so for instance, the fact that this response is oscillatory, right, and the fact that this response is not oscillatory. If you think about the math you would have to do to actually calculate these, or let's say to figure out the nature, you'd be thinking about the poles of that closed loop function, right? And here, this is a piece of thing that I expect everybody here to know, right? That the characteristic equation for the closed loop responses for any input into the loop is the same, right? We derived that, like I've spoken about it, like you can go back to the videos, I accentuated it very strongly then as well. What that means is that whether you're going from the set point or whether you're going from the disturbance, the denominator of that closed loop transfer function is the same, which means the characteristic equation is the same, which means that the roots of that characteristic equation are the same, which means that the dynamic nature, the qualitative behavior of those signals will be the same. And so, while they, when you know, so to a certain extent, what do you mean when you say, do they look the same? One way of interpreting that is like, do they have the same dynamic characteristics? And the answer is 100% yes, both of them will have the same dynamic characteristics. If there's oscillation in the set point response, there will be oscillation in the disturbance response. If there's no oscillation in the set point response, there will be no oscillation in the disturbance response, and so on and so on and so on, because it's the same nature, it's the same poles, it's the same characteristic equation roots, okay? Let's say the obvious differences are that for a disturbance, all things start at 1, and there's like, let's say, you just have to think about reasoning through it. If you wanted to add a disturbance to that, and here, look, I mean, to some extent, it's not 100% true to say that I'm not relying on any memory at all, because like I can't forget all the times that I've seen what these responses look like. So at least some of this is like, well, I know that this is kind of how it's going to look, but you can reason, you really can reason through it. So if there's a disturbance of this nature, so in other words, if I just have a D entering there with no extra transfer function, then again, kind of what I would say, obviously, although I quite hated it when lecturers said that when I was a student, but if D makes a step like this, then Y will at least initially make a step like that also. Right? So as soon as D changes, because Y is equal to D plus whatever this signal is. And again, just reasoning through that, like at that moment, at the moment when the disturbance steps, Y prime is 0. At that moment in time. And so at that moment in time, the disturbance will jump, or the output will jump immediately from 0 to 1. Again, just because of how math works. This is not, again, like it's not a control thing. It's just understanding like what those formulae actually mean is when D changes, at the moment that D changes, that becomes 1. And so that's just inevitably drawn through to Y, because Y is just at that moment when Y is equal to, so I mean, conceptually you can see what's happening here. At that moment, at T0, when Y prime is 0, then Y is just equal to 0. And so we expect exactly that kind of behavior. But at that same exact moment, right, like now Y is equal to 1, that means E is equal to minus 1. Is everybody following that? Again, just because of math, right? So if at a certain point in time, D is 1, so, I mean, all of this, like, forget about the time function and just think about it. At a given moment in time, if D is equal to 1 and Y prime is equal to 0, then Y is equal to 1, right? If Y is equal to 1, and remember we started off with Y as P equals 0, at that moment in time, at that same moment in time, E will be equal to minus 1, because 0 minus 1, no, wait. That's why nobody understands what I mean. No, yes, it's true. Yes, it is minus 1 exactly. So 1, and then Y is P minus 1. 0 minus 1 is minus 1. So at that moment in time, right, I'm now seeing an error, and that means that the controller will now take action, but now in the negative direction. And again, at that moment in time, with this particular GC, that means this will be minus 5, right? And then, so that initial behavior will be much the same, except that the system will be pushed in the opposite direction. Is that making sense? So this is kind of the thought process that I'm imagining you going through whenever you see these graphs, those qualitative graphs, right? I'm imagining you kind of reasoning through that block diagram in this way. Any other questions? So, look, wind-up is not a linear effect. So that is only if there is, I think that's probably better if I record a different video on that. But like, actually, you can just go back. I've spoken at length about wind-up. I'll just go and find the lecture. But like, I've spoken a lot about wind-up in a previous lecture. And let's verify that we did everything right qualitatively. When I was working out this notebook now, I noticed that the value of tau I that I had in the video, which was equal to 10, didn't really result in the amount of oscillation that I drew in the video. So I've used tau I is equal to 1 to get the same results as in the video. So just keep that in mind. It's a qualitative graph. Remember that in a test situation I would specify values in such a way so that you would be drawing this caricature version so you wouldn't be penalized if you hadn't got this right. But I'm just using the control library over here. So one of the things that we did in the when I was sketching is I was reasoning through the point where the error became 0. and I'm finding the point where the error becomes 0 for this particular feedback loop in this way. I've just got a general plot response thing here, and I'm trying to match everything to the video over here. So just to show what we have over here the set point, over here in green the open loop response, in red the response of a proportional controller with KC is equal to 5, and in teal the control response of a PI controller. And you can see that that's roughly the kind of response that I was drawing in the previous part of the video. Everything kind of matches up over here. You can see that the error, the rate at which we increase the error integral does have roughly the shape that we were talking about. One thing that's slightly different here is that there's actually an increase in the output over here, which corresponds with this large value of the integral that gets carried through. I just want to show as well what it looks like when you have a time constant equal to 10. This is important because it's important to notice that it's possible to get non-oscillatory response with a tau I controller. So this looks very much like a non-oscillatory response. You'll see that there is actually a point at which the error becomes 0 at that point. So there is actually a little bit of oscillation, although for practical purposes it's almost nothing. But we can still see all the same kinds of properties. So we can see that the closed loop response is much faster because of the larger magnitude of the input. So we can see U here is 5 at that initial point in time. And we can see that the version with the integral goes to 0, where the version with proportional does not go to 0. So that's a good confirmation of these results. I'll link to this notebook in the video as well.